All right, class. Welcome. Today, we're going to conduct a deep dive into one of the most critical concepts you'll encounter in business finance, the present value of an annuity. Now, I want to be clear, this isn't just some abstract formula to memorize for an exam. This is a powerful, practical tool for making major financial decisions, both for your own life and certainly for the companies you might one day lead.
So let's start with a question that, trust me, every single one of us has to confront eventually. How much money is enough to actually retire? This isn't a number you can just guess at or hope for the best. It's a figure that we can and must calculate with a great deal of precision. And the concept we're talking about today, the present value of an annuity, is exactly how we're going to do it.
To get to that answer properly, here's the roadmap we'll follow. First, we'll unpack the problem itself, what we call the retirement conundrum. Then we'll look at the blueprint for solving it, before decoding the formula piece by piece. After that, we'll see the calculation in action. And finally, we'll discuss some common pitfalls to watch out for.
So, let's talk about this conundrum. At its heart, the fundamental problem in retirement planning is this. You spent your life building up a finite amount of savings, your nest egg. But you need that finite pile of money to generate income for a period of time that is, well, it's often unknown. The primary challenge? The thing that keeps people up at night is managing that cash flow to avoid the truly terrifying risk of outliving your savings.
Now, to solve this very specific problem, the financial world created a very specific tool. It's called an annuity. At its core, an annuity is simply a financial contract that takes a lump sum of money and transforms it into a steady, predictable stream of future payments. It's so fundamental because it provides certainty in a very uncertain future, which is exactly why it's central to both personal planning and huge corporate pension funds.
Okay, so how do we figure out just how large that retirement fund, that lump sum, actually needs to be? Well, for that, we use a specific formula. But I don't want you to just think of it as a bunch of letters and numbers. I want you to think of it as a blueprint for financial security. Or, even better, think of it as a time machine for money. It lets us look into the future, see the stream of income we want, and then it tells us exactly what that future stream is worth in today's dollars. And this all hinges on one of the most important principles in all of finance, the time value of money. The idea that a dollar you have today is worth more than a dollar you get tomorrow, simply because today's dollar has the potential to be invested and earn interest. So what we're doing here is not just adding up future payments. We are calculating the single lump sum needed right now, which, if invested, will grow and be sufficient to fund that entire stream of future withdrawals.
Okay, let's pop the hood on this formula and really examine it piece by piece. My goal here is for you to understand the logic behind the math, not just how to mechanically plug in numbers. Each variable in this equation tells a crucial part of the story of your financial future.
First up, we have PV, or present value. This is our goal. This is the unknown variable we are trying to solve for. It's the answer to the big question, how much money do I need to have saved and invested on day one of my retirement? This is our target number.
Next is R. R represents the regular payment. In financial jargon, it's sometimes called the rent. This is the income you want to pull out of your account each period, whether that's monthly or, like in our example today, annually. So R really represents your desired lifestyle in retirement. Now, the variable I, this is the interest rate. And I want you to think of this as the absolute engine of this entire model. Your nest egg isn't just sitting under a mattress, right? It's invested. And I is the rate of return it's expected to earn. This growth is what allows your remaining principal to keep generating income even as you're taking money out. A higher I means you need less money up front. A lower I means you'll need a lot more. It's incredibly powerful.
And finally, we have N. N represents the total number of periods, or the total number of withdrawals you plan to make. In our retirement example, this is simply the number of years you need this income to last. This variable quantifies the duration of your plan, and as you can imagine, it has a major impact on the final calculation. A longer retirement requires a significantly larger present value.
So, when we put it all together, we get this formula. I know it might look a little intimidating at first glance, but now you understand every single component. We have R, our desired payment, and that big piece in the brackets, that's what's known as the present value interest factor of an annuity, or PVIFA. You can just think of it as a special multiplier. It tells you the value of a stream of $1 payments discounted back to today. We then just multiply that factor by our actual desired payment, R, to get our final answer. It's actually a very elegant piece of financial engineering.
Okay,
Theory is one thing, but let's get our hands dirty. Applying this formula to a real-world scenario is where the concept really solidifies and starts to click. Let's see it in action.
So here's our case study. We have a retiree who wants to withdraw $30,000 every single year for 25 years. The retirement fund is invested in an account that they believe will earn a consistent 4% annual interest. The question, then, is what does their account balance need to be on the day they stop working? What is our PV?
All right, let's solve this together, and we have to be very careful with our order of operations here. First things first, we solve what's inside the deepest parentheses. We calculate the discount factor. Then, we take that result and subtract it from 1. After that, we take that whole top part of the fraction and divide it by our interest rate. That gives us our big PAVFA factor. And the very last step is to multiply that factor by the $30,000 annual payment.
And after you punch all those numbers into the calculator, the answer you get is $547,707. Now, I want you to just think about that for a moment. To generate $30,000 a year for 25 years, even with your money still earning a 4% return, you need to start with over $500,000. This calculation really highlights the immense scale of the financial challenge of retirement.
Now this brings me to a really important discussion. Let's talk about where things can go wrong. Because in business mathematics, a seemingly small error in your calculation can have massive, sometimes multi-million-dollar consequences. Precision isn't just a good idea, it is absolutely paramount.
One of the single most common mistakes I see students make is a mismatch between the interest rate and the payment period. For example, if you have monthly payments, you must use a monthly interest rate. You can't just plug in a 4% annual rate if N is, say, 300 monthly payments. You have to take that annual rate and divide it by 12 first. It's a critical and very easy mistake to make. And of course, simple things like messing up the order of operations or rounding your numbers too early in the process can also completely throw off your final answer.
And this is exactly why this isn't just an academic exercise for a grade. As a future business manager, you'll use this same logic to evaluate whether a new factory or new product line is a good investment. As a company leader, you have a fiduciary duty to ensure the corporate pension plan is properly funded. A miscalculation there could jeopardize the retirement of thousands of your employees. The stakes in the real world are incredibly high.
So I'll leave you with a final thought to take away from our lecture today. Our entire calculation, our whole $500,000 plan for this retiree, it all relies on one very clean, very neat assumption: a stable, predictable 4% return, year after year. But what happens in the real world of fluctuating stock markets? What are the implications if that return is sometimes positive 10% and other times negative 5%? What happens to the plan when our tidy assumption is wrong? That, class, is a question of risk management, and it's a topic for our next discussion.